My project is on malware detection. For context, I've worked in digital forensics for the past 4 years and looked for malware in logs daily. I wanted to see if a machine learning algorithm could do the same. The key question I'm trying to answer is, in Windows event logs, is a given record benign or malicious? And this classification between good and bad forms the backbone of computer forensics. This problem is particularly important because cyber attacks are only getting more and more frequent, and this kind of work could help detect attacks, leading to a clear societal benefit of increased digital security. I chose Windows event logs specifically as my evidence source simply because they're the most common. Automated malware tools do exist, but they work based on signatures of known malware, so they can't keep up with new malware, which comes out very often. I want to see if machine learning offers a viable alternative. You can think of Windows event logs as very detailed timelines of everything that's happened on a computer. I've displayed an example of what my processed logs looked like. In addition to default fields, I created an additional one called base64 encoding, and the value was populated with 1 if long base64 encoded strings exist in the message field, like in row 3. This sort of activity is a clear giveaway of something malicious going on. To create my training data, I classified each row manually with my team, who are all forensics experts. Each row was assigned a classification, which the model will do too. We classified approximately 10,000 rows of data, and that formed the dataset for this project. The first baseline I implemented used the interquartile range to identify anomalous event IDs. I then looked to implement a simple LSTM. This used 2 features. I used unigrams and bigrams of words for the message feature and label encoding for the base64 feature. I chose an LSTM because it's particularly well suited to time series and decided on an Atom optimization algorithm because it's particularly good for neural networks. My main approach involved using a complex LSTM, and I added more features. The final extension was to use a BERT model for the message field and optimize this and the LSTM concurrently. I think one of the most interesting parts of this whole project was the fact that we were using lots of different types of data, language and numerical data. And this final setup was a really good approach to tackle it. The basic statistical approach gave an overall accuracy of 69%, but a malicious accuracy of 0%. You can see that the second metric gives more of an indication of how basic it is, and it ended up classifying all events as benign. In terms of the simple LSTM, the accuracy numbers are really high, but this is actually quite misleading. These tests revealed an issue in my data and methodology, so we need to note that any data with base64 encoding is trivial to classify. It's always malicious. And in my test data, it ended up being a sample where 97% of malicious events included encoding. So 97% of malicious events were trivial to classify. But what I want to focus on in this project is the non-trivial classifications. So I decided not to include base64 encoding as a feature, and I also carried out tests removing any encoded records from my dataset. My main approach ended up using a complex LSTM without the BERT model. So it was just a complex LSTM with 5 different features. This was only because the BERT model ended up being too computationally intensive for my setup, given the time. But it is something that I will look to do in the future. The results are definitely promising, with high malicious and overall accuracies. And you can see the training loss going down in the graph on the right-hand side. This also did introduce false positives, which is something to be aware of. In addition to what's already been mentioned, I think the key challenges involve the training data. So there's not a huge amount of stuff available open source, and any client data is wrapped up in confidentiality. Also, there are far fewer malicious events than benign events in my dataset, and this proportion varies considerably on a case-by-case basis. So we need to think carefully about weights for different classes. I think this project has shown a lot of promise. It's been really enjoyable to work on, and I'm looking forward to doing more work on it in the future.